start whenever you're ready.
Okay. I just did, oh, there it is. All right, so this is lecture 2 on axiomatic design. And in this lecture and exercises, we're going to be going over decompositions. And so what we want to do is provide structure to the design problem. And so this is analogous to setting up a vector sort of force diagram for a free body diagram in a mechanics problem. So let's see how this goes. Decomposition is a fundamental concept that we use in lots of different things. Somebody serves you a steak that's too big to fit in your mouth at once. You have to cut it up. It's a kind of decomposition. So it helps to break work up into little chunks. And we need to do that often to solve all kinds of problems. So just like when we do a free body diagram and put a vector into fx, fy, fz, when we look at a design problem, we start at a high kind of general level, and we have to figure out how to decompose that. In a way, the solution is already there, and it's just for us to break it up and figure out what we're calling it, essentially, at the finer and finer levels. So the structure of the design is developed during this zigzagging decomposition process. And one of the things is we need appropriate prioritization as we're doing the decomposition. So let's see how this goes. All right, so we have, and we talked in the first lecture about domains, and now we're going to stress a little bit more on hierarchies and how these things work. We talked about the mapping that we have from FRs to DPs, and we also started with the customer needs. How do we get to the FR? And then we talked a little bit about going to the processes, but for today we're going to be emphasizing this middle part right here, FRs to DPs. The hierarchical decomposition is when we take FR1 and break it down into 2 or more components, which we would call FR 1.1, 1.2, 1.3, and so on. There's one other thing that we need to know about, and that's constraints, and those apply to the FRs and the DPs and the process variable, and we'll talk more about that later. There are two kinds of decomposition that I like to talk about. One is horizontal, and that is into the domains. That's the horizontal part. And the other is vertical, and that is the hierarchies. So we've got 2 directions for decomposition. So what we're going to concentrate on is, as I said, that middle part. And you can have any number of elements into which, say, FR1 is decomposed, except 1. If you decompose FR1 and you only have 1 element, then you really haven't done a decomposition. You may have just done a renaming, or you may have forgotten something. Notice, too, that we have a one-to-one correspondence between the FRs and the DPs. Now, that little space shouldn't be there. But, all right, so recognizing that, I don't know how they've got there, some kind of Microsoft magic. But we notice that if we've got 3 FRs, we've got 3 DPs corresponding. And we'll be talking about the reason why you need to do that. Actually, we touched on that last time. So as we do this vertical decomposition, we start off with something like say a concept S, and then it's like a set, and we're going to decompose this into its components 1, 2, 3, and so on. Now, one of the things we need to have, of course, in a good decomposition is that if I take all of the components and add them up, I get the combined set, or the union of that, and that's what we have here. The other thing that's important is that these elements, 1, 2, 3, and so on, or like I and J, are completely independent. So we have essentially strict little lines here that define where these borders are, and there's nothing in SR1 that ends up in SR2, and nothing in SR2 that ends up in SR1. And that's what this equation means here too. So this one says we sum it all up, we get the whole, and this one says that none of the elements are overlapping. So what we're doing in the decomposition, essentially, is just explaining or articulating what the details are, the contents at each level. It's done by a zigzagging process. So we start with FR0, and then we need to figure out what DP0 is. So FR0 is our upper level, top level objective for the design. Here's what we're trying to do. DP0 defines how we're going to do it. And so then DP0, after we do DP0, then we can, so we zigged, now we'll zag back, and now we do FR1 and FR2. Now DP0 is a special kind of constraint, provides a constraint on FR1 and FR2. Let's say FR0 was manufacture crankshafts, and then so DP0 is sub it to a factory in China. All right, so now FR1 and FR2 will be based on what we've chosen for DP0, and will have something to do with how you manufacture something when you've subcontracted it overseas. Now, suppose DP0 was manufacturing a factory in Worcester. Now, FR1 and FR2 would be much different, because then you're taking sort of direct action to manufacture it where you are. So after you get FR1 and FR2, similarly now we're doing DP1 and DP2, and then once we get DP1 and DP2, we're going back and decomposing FR1 and FR2 with a constraint of DP1 to generate 1.1, 1.2, 1.3, and so on. And then do the same thing with DP2, and then select DPs to match those FRs. FRs, these are very special, and we need to make sure we know when we've got good FRs. So here's some simple things. They begin with verbs, and they're in the imperative form. So everything in the imperative form begins with a verb. So for example, limit motion to the x direction. So the verb here is limit. And then another one would be transmit loads. All right, so transmit loads. Transmit is a verb, and loads, it's in the imperative form. So you can see that applies to all of these. Now, what do the FRs do? We need to take the CNs, the customer needs, and translate those into engineering terms. So when you go to produce something for somebody, they may have a whole list of things that they would like you to do. I know I went to a workshop on axiomatic design several years ago, and they're talking about making software for the military. And they would have a list of over 1,000 things that software was supposed to do. This is almost 20 years ago. And so they said, what are we going to do with that? And the answer, as we discussed it in this workshop, was, well, you have to go through and see what kinds of things have they given you. Some may be easily translatable into FRs. They may actually tell you that this software should calculate something, and that's clearly an FR. Some of it might not be so much an FR as as a constraint. 20 years ago, maybe they had some old computers. They might have said a constraint is don't use any color because we still want to use our black and white screen, something like that. So you can sort through the customer needs and see that some things really are good as FRs. Some might be lower level FRs. Some might be upper level FRs. So you sort of have to work through and see what they are. Some might be, for example, military says produce in the United States. All right, so that's not really an FR, it's a constraint, or maybe it's part of your PVs, depending upon how you formulate your design problem. In any event, we take the customer needs and try to translate those into engineering terms, and some of those fit well as FRs. So these are, they need to be capable of having tolerances, performance or, say, functional tolerances. So some sort of performance or functional tolerance. We want to formulate these in a solution-neutral environment. So we don't want to sort of jump the gun with how are we going to fulfill this FR. Let's figure out the FRs that are going to make this product or this process the most valuable, and then we'll sit down to figuring out how to fulfill them. But if we sort of jump the gun on the DPs and say this won't work because of this, or we need to do it this way because of that, we may miss the best solution. It's interesting working with the design team that doesn't have the habit of doing this, and I find that these design teams have kind of a vague idea of what the objectives are. People start shooting out different kinds of solutions, different DPs, until something sort of, oh, that sounds nice, let's try that, and they find themselves well on the way to a solution without having clearly stated what the problem is, and decompose that in such a way that you can find the right solutions down to the sort of the nuts and bolts, nitty-gritty kind of level. So it's important to know where you are going, right? So people sort of trying to find, oh, what's the solution to the problem, and engineers, you know, like to think, I've got a really clever idea, before we really have stated clearly what the problem is. You need to know where it is you want to go. Otherwise, you won't even know when you got there. So if you haven't clearly stated the problem, you won't know when you've solved it. Here's another important thing. You need to define the design objectives. How are you going to measure or evaluate the success of your design? Well, if you have the FRs and say, here's what it's supposed to do, then you can say, all right, well, I'm going to test or measure this and see if it does it. The other important thing about the FRs is they are the design intent. Here's what we want the design to do. So we record and decompose at every level the design intent. What is it that we're trying to do? So often you look at a drawing and that doesn't have the intent somehow recorded on it, and you're saying, what is this little feature for? What does that do, right? If you have a good decomposition, it goes with the drawing, you can say, I see. This is what this is supposed to do. That's what that's supposed to do. Without knowing the intent, we can't change things. One person that worked on axiomatic design said, you know, we could build another Saturn V moon rocket. We have the plans. We know what goes into it. We couldn't change it. We don't know why those things are there. So without knowing the design intent, nothing can safely be changed on a design. And very often you get a product design that's going to manufacturing, and you're saying, does this inside corner really need to be square? And if the design intent is there, it says, yeah, it's going to block something in there. You go, all right, so we'll go to the trouble of making a square inside corner. Now, in the first lecture, we talked about the FRs being independently controllable. So as you figure out what they are, as you say, geez, is this an FR? You go, is that something that is so important in this design that we need to be able to control it? As temperature changes or whatever it is changes, is this something that needs to be adjusted so we get the outcome and we provide the customer with what they need? So, so the FRs are what we're designing to. The FRs are there. A design will be no better than its FRs. If you choose the wrong FRs, you're not going to have a good design. All right, FR0, the top one, sets the theme. That defines the overall direction. Now, one of the things you have to do is you have to invest more time in the top of the hierarchy. Unfortunately, in many ways, progress in design is often judged by how quickly you get the drawings out. The drawings are nice and they're important to have, but often you start doing the drawings before you really know what the intent is and you've really figured out, all right, what is the upper level, stuff, what are the best concepts to develop to satisfy this design problem. Once you have something invested in the drawings too, it becomes harder and harder to change it. So what you want to do to take advantage of axiomatic design is invest some time at the top of the hierarchy. Make sure that you've got there what you want. Now, one of the reasons why it's worthwhile to invest the time at the top of the hierarchy when you're using axiomatic design is that the axioms allow you to evaluate the design at the abstract levels to find, to choose the best concepts to go forward with. So you can start to see already at the abstract level if something is violating one of the axioms, and if it is, then let's develop a different concept and go with that. So recognize the value of good upper levels in the hierarchy, and you've got to get the customers on board. Now, one of the things we're going to be going to in a little while is a ski binding, and I thought I had that corrected, so my apologies. What I would actually like you to do at this point is go instead to the shaft surface that we talked about in the first. And let's see, I can't talk and spell at the same time, apparently. So go to that shaft surface problem for the rotary lip seal and say, all right, so what is the top FR and the top DP for the rotating lip seal? And so yesterday, in the other lecture, it was what are the customer needs. Now take a look at those and see if you can get in one sentence, without a conjunction if you can, what the overall objective is for the design of the piece itself. And then how are you going to satisfy that with the DP0? Now the review we'll have to we'll do later when we can get together and talk about this. A good decomposition. What we were developing earlier can be summarized in terms of a good decomposition really is C, me, min. C, me, C, CE, collectively exhaustive. All right, we want to know, did we think of everything that we needed to think about? So this is the first part of this. If I add up everything, all the children in the decomposition, will they equal the parent? If it's less than the parent, then I'm missing something. And if it ends up being greater than the parent, the sum of the children is greater than the parent, then I've added something that wasn't in the parent. We might go back and say, geez, I think I really want that. Let's go back and redefine the parent so it includes that. Or it might be, you know what, we don't need that thing because it wasn't part of our objective. So the sum of the children to equal the parent, the children must be a collectively exhaustive decomposition of the parent. All right, the next thing is to make sure there's no redundancy or overlap. So now we want the me part, C, me, M, E. So if they're not mutually exclusive, you will not be able to satisfy axiom 1. And we'll talk about that more in a minute. And then minimum number. There are situations where it can seem like you're collectively exhaustive. It seems like you're mutually exclusive. But then you go and look and you say, I think I don't need all of these. And I think I can satisfy the upper level FR with less than that. Now, this concept of see-me in particular is, has been used in other places, and management consultants have talked about me-see instead, and they've just reversed the order, and they put the mutually exclusive before the collectively exhaustive. For engineering problems, I like to have the collectively exhaustive first. Did you think of everything that needs to be done? And that's part of an engineer's job. Right? What do we need to do if we're designing this machine? We need to be able to position the tool. We need the safety of the operator. We need stiffness. We need to worry about vibrations. We need to make sure we've thought of everything. So sum of the children equals the parent. So as I said, when you start off with the upper level FR, you essentially have everything there, and what you're trying to do is just figure out how do we break it down so that it becomes more manageable and easier to understand. So collectively exhaustive, sum of the children equals the parent. So no single child decompositions. I talked about this before because if FR1 decomposes into just FR1.1, then you haven't decomposed anything. So mutually exclusive. So as I look at FR1, 2, and 3, they're all separate circles. They all define separate space so that they are not overlapping. If they are overlapping, so if FR3, for example, went out like that, then when I start to change FR3, I'm going to do something to FR2 as well. Oops, let me see if I can repair that. So FR3 and FR2, if they have this area in common, some changes in FR3 will result in a change in FR2, and so I won't be able to make them independent, and therefore axiom 1, the independence axiom, cannot be satisfied. All right, spoke about the free body diagrams. So we have a force F like this, and we're going to decompose that into 3 components. So Fz, there's Fz, Fy, right, and Fx. And if we add those 3 components together, we get F. So the free body diagram is an example of a collectively exhaustive, mutually exclusive, minimum number decomposition. It's a good decomposition. All right, themes for decomposition. So one of the questions we posed in the first lecture is, have you thought of everything? Did you figure out everything you needed? And then, how do you know that you thought of everything you needed to think about? That's a tough question, and as your experience in a certain problem will help you to tell you if you know, but also figuring out the right theme, and we'll get back to that. Mutually exclusive. How do you know if things are distinct or separate? And minimum number. How do we know we don't have more than we need? So let's start taking a look at some of these things. If we have a good theme, then it's easier to tell that we are collectively exhaustive and mutually exclusive. So you might break things down in time. You might break things down in space. You might break things down in terms of the kind of energy. You might break things down in terms of the components. If you're manufacturing some kind of product, you say, all right, we need to manufacture this part and this part and this part. And, of course, there's other kinds of themes that you might be able to think about. The other thing that you can do with other is that you can do the decomposition, and if you know if you're missing something, you might be well to kind of admit it and say, all right, FR 1.6 is other. And then you've kind of just kicked the problem down the road and say, all right, well, now I've got to figure out how I fill up other. All right, let's take a look at an important kind of manufacturing problem relates to safety in the machine shop. So there's 2 themes that we might use to decompose it. One would be sort of a spatial kind of theme. Let's protect each user at each machine. Another kind might be energy type. Let's protect people from electrical energy, mechanical energy, thermal energy, different kinds of things, kinetic energy, it's a different form of mechanical. So here is the energy, and here is essentially the spatial theme. Now, one of the interesting things is that after we say, all right, let's protect them at each machine, how do we know we're doing a good job at that machine? Well, we could look at all the different kinds of energy that are at that machine. And we say, geez, how do we know we've covered all of the places where somebody might be able to absorb some kind of energy, electrical, mechanical, thermal, that would be bad for them? Then we could say, well, let's take a look at the, at the energies in each machine. So the interesting thing here is it looks like it might be communicative. In fact, when we get down to sort of the nitty-gritty level, we end up with a bunch of devices. So acoustic, energy, it's protecting people from different things. And so sometimes the composition path doesn't matter. The low-level DPs are going to be what they need to be at some point, and you can get there by a couple of different routes. But some routes may be easier or more obvious than others. Some routes may avoid some extra work. So, for example, some machines, if we take this example, some of the machines may not contain certain kinds of energy. Thermal energy may not be a problem at some kind of machine, for example. So, after I get to that machine, I can say, well, there's no thermal breaks on this machine. There's nothing that's going to get hot, so we don't need to worry about it. Okay, so once again, excuse me, somehow this escaped editing. We'll get to the ski binding in a moment as a kind of case study. And the other thing that had actually gotten edited and then my computer crashed. So I want you to work for about 5 minutes, but since you're probably watching this by yourself, don't worry about the groups. And so see if you can come up with some children for the shaft surface and some children of FR0. All right, so after you do that, so now, so if you've taken a small break, or if you haven't, it might be time to do it. See if you can come up with the upper level of functional decomposition. And now, how do you know it's CME min? Well, that's the first thing you want to do is test. Collectively exhaustive. Did you include particularly all value-adding elements, everything that you need to have in the shaft surface in order to provide a proper interface with the seal? So what kinds of things would you want there? So the shaft surface, let's think about what the upper level FRs might be. So we'll do a little review, and you might have a different solution that might be just as good. So FR1 might be to provide a seal, and FR2 might be to provide a low wear counterface. Now, you should be probably entering this in a Claro and getting used to working with a Claro. It's a pretty intuitive program. So then the question is that collectively exhaustive? Is there anything else that shaft needs to do? So low wear counterface, provide the seal. All right, so let's see, FR1, it won't leak. FR2, it's not going to wear out. Does that satisfy your customer needs? Or it won't wear out any more quickly than it has to. All right, so mutually exclusive. Are there can these two be satisfied and controlled separately? All right. And so sometimes what we're doing is we could say, geez, I could think of a way those would interact. And so then, but that's not what you're trying to do. You're trying to think of design solutions where they won't interact. So, so I think we can manage to do that. Minimum number. Well, if I had any fewer, I'd have one, and I wouldn't have a real decomposition. So, so it's important here that at least 2 is the minimum number. Otherwise, I didn't need to do a decomposition. So is there equivalent value in fewer? I don't think I can eliminate either one of those. So that decomposition could be C min. All right, so now the upper level DPs constrain the lower levels. So we need to, one of the things we can do is use kind of placeholders if we don't know what the upper level DPs are. So in this case, the upper level DP is going to be the topography of the shaft surface. But we might have some other things and some other sort of design concept. And so we could say, well, we need a system for something, or a component for something, device, method, module. So, so what we do essentially is fill in this blank with whatever we derive from the FR that fits in there appropriately. So, so it could be as simple as, let's see, a module for providing for a seal. That doesn't tell you much about how you're going to solve the problem. And again, all you've done is kick the can down the road, say, all right, I got to pick up this at the next level down and start figuring out how I'm actually going to do that. But the decomposition can help lead you to solutions, and that's essentially what you're trying to do. Decompose it till the solution is obvious. So sometimes what these generic kinds of decompositions can do is essentially expedite the decomposition of the higher levels. Then you can go back. Ah, here's where I did manage to change ski binding to shaft surface. So, so now we want to find, but I didn't get the groups part. So unless you're watching this with somebody else, it's unlikely you'll be able to form a group. So, so see what you can do to select the children of DP0, the topography of the shaft surface. So are there different aspects of the topography that you can use to satisfy FR1 and FR2? All right, so you might take a few minutes to do that now, and then and hang on to that. So we only had 2 FRs, and if you don't know much about surface roughness, this may be difficult to do, but it's essentially a geometric problem. And so you may find some ways of describing the kinds of geometry that you think would work for this problem. All right, FR0. Let's take a look at this case and say we have a design problem where we want to provide a ski boot attachment for safe skiing. So one of the things it needs to do is transmit control loads. I can't ski safely if I can't transmit control loads to the skis. In skiing, it's the ski-snow interaction that provides the forces for changing direction and for stopping. And the interesting thing, actually, in the context of a manufacturing processes class, is that the ski is essentially acting like a tool and machining the snow. Here's the chip flying up there. And so if we take a look right in there close, what the edge of the ski is doing on the snow, it's acting essentially like a tool, scraping the surface of the snow. And we may get a chance later in the class to talk about how skiing is like machining, which is an important manufacturing process. But in any event, for right now, here's an interesting thing. We want the skier to be able to transmit control loads through the boot, through the binding. We'll take a look at bindings in a moment, in order to change direction and provide control. Now, this is an interesting and one of the more complicated human-machine interfaces because of the exact nature of the control that you have to be able to exert to be able to manipulate ski courses or get down to ski courses. So here we have the chip flying up, ski acting as a tool, machining the snow, and that's where the forces are coming from. In skiing, you need to be able to control the edge angle well, and that's why you have the stiff boot. And fore and aft forces. So we need a boot that's stiff this way, and then we need a boot that's stiff this way, so we can exert fore and aft forces as well on the ski. And the binding, when we see the toe piece of a conventional binding there, is what's providing the interface between the ski and the skier. Now the FR said safe loads, and so anytime we have a human-machine interface, particularly where force is used in the control, so this could be lots of hand tools. What are we doing to make sure that injurious loads don't get forced back? But you could open another Aclaro file here and say, all right, how am I going to decompose the control load transmission branch in this decomposition? So again, since you may be watching this at home by yourself, don't worry about forming a group. So work for about 5 minutes and try to figure out how could I decompose the load transmission, control load transmission, which is FR1. So develop the children of the children for FR1. So this is the children of FR0, children of the children of FR0. But I'm not sure why I have that twice there. All right, so if you haven't, take a short break, see if you can figure out how to transmit the control loads. And again, here's the test. Collectively exhaustive, mutually exclusive, minimum number. So every time you go to review a design, you want to go through this see me min. All right, so see if you can find the elements that are going to satisfy the children of DP1. So if you haven't, you might want to take a short break. If you're not, and try to get those elements. Here is a picture of a relatively modern ski binding in the upper right, and then some pictures taken from patents. The basic ski binding technology has not changed in about 40 years, as you can see from the age of some of these patents, of the most popular kinds. So there's so as we're looking at transmitting control loads, the control loads have to be transmitted through interfaces like there and there, that where the boot presses against either the ski or there and there where it interfaces with the binding. So transmitting control loads, and actually look for those are surfaces that are oriented in certain directions at certain places. So if we take a look at this, all right, so here's transmitting the control loads. So we've done this as a separate problem with this being FR0, but you can renumber it as you like. And the DP is going to be some kind of interfaces, mechanical interfaces with between the boot and the binding. So transmit forces. Well, we suggested that this looks like a free body diagram. So we've got X, Y, and Z forces. And then, so how do I transmit an X force? Well, I need some sort of interface. If this is the X direction, I need some sort of interfaces like that so I can push against something that's attached to the ski with something that's attached to the boot, and then I can transmit a force in the X direction. So what does that look like? Some plane in the YZ, oriented in YZ. So similarly for the other three. So there's Fx, Fy, Fz. So we think, well, I get 6 degrees of freedom. What am I missing? The moments. So, so I'll transmit forces and transmit moments. That way I've transmitted all the loads. And then, so if I need some sort of structure now to transmit what I'm calling a structure, to transmit a moment, because I need a lever arm and a force. And so I can think of a couple and then some distance, a force couple, and then some distance between those. So a couple transmission structure about the x-axis, for example. So we're transmitting the moment through a couple, which is how you do this mechanically. All right. So now we figured out, geez, all right, so I've got to transmit loads across an interface, and so here's some structures I need to do that. So transmitting loads is a common problem in mechanical engineering. All right, test for minimum number. So we look at the next level of a decomposition where we're transmitting moments. We provide a lever arm and transmit a force. So we get the lever arm and the force. Well, this is transmit a force. Well, we're just talking about that. YZ plane, YZ plane. If we can transmit the moments, we can transmit the forces. The opposite is not necessarily true. But because the moments require a lever arm and a force transmission, this seems redundant. So we have, as you can see here, the same dP. So did I really need those? Maybe I didn't. So in fact, in many kinds of problems like this, unless there's a large force without a moment, the structures to transmit the moments may be sufficient to also transmit the forces. All right, let's take a look at another case, minimum number. So there was a case where it looked like we were CME min, or CME anyway, but we weren't min. And so we could accomplish the design function by getting rid of some of the, still accomplish it by getting rid of a whole sub-branch there. All right, so what if our objective is to prevent some vessel from exploding? We could use an energy theme and say, all right, we want to keep this thing from exploding. Something like, say, a battery in a computer. You don't want it to explode. And so we might say, all right, well, let's, if we think of all of the ways that energy might be able to destroy something, let's see. So all the different kinds of energy. We could have chemical in a battery. We have electrical. We could have thermal. And we could have a kind of mechanical due to pressure. So if we wanted to prevent something from exploding, we could say, all right, let's prevent all four of these things from happening. It might cause something to explode. But at the end of the day, if we think about this, what really causes things to explode? It's a pressure differential. So if we have more pressure inside than outside, and to a degree that's large enough to compromise the vessel, it will explode. So, so all we really need to do to prevent an explosion is look at the pressure part. So the chemical, electrical, and thermal energy, if they can act somehow to raise the pressure inside the vessel, then that could be caused to explode. All right, let's take a look at a decomposition that's done as part of a WPI project to make a jig grinder, actually turn a CNC milling machine into a jig grinder. So what's a jig grinder do? Here we're looking at the business end of the jig grinder, and it whirls around and goes up and down. So it's turning like this, round and round, and then moving up and down in a kind of jigging operation. And what's it used for? Well, if I've got something very hard, like this piece must be here, and I need to get a hole just the right size, I take this little shaft that we can see here. Let me clean that up. And so this is going to have some abrasive attached to it on the sides. Then when it gets in there, it can move up and down, move around. And if I know where those sides are, and that's spinning around, and I've calibrated everything, I can make a very precise hole in something that's very hard, and that's what's going on there. So we have the jigging going up and down. We need some positioning for Z, positioning for X and Y, and then this thing has to rotate, usually rather fast, because to get good tangential speeds at the surface, with a small diameter, you need a high number of RPMs. New England Machine Tool Company makes a jig grinder, and there's an example of that. And so, but the customer we had wanted to have something less expensive, and so they thought, I wonder if we can do this with a Haas mini mill. So the idea was, let's make an attachment that is going to supply the jigging motion. They said, use an air spindle to get the highest RPM, and then attach the whole device to the Haas spindle for positioning. So there's a Haas mini mill, and the idea is, let's stick a device in there. So develop the high-level FRs and constraints from the customer needs. Select the corresponding DPs. Check for coupling in violation of the cons, the constraints. And so check for coupling. Coupling is axiom 1. And then go to the next level. So when you go to review a design, here are the steps. After you develop these, you need to, I guess you develop the DPs at the same level. Then you check for coupling, and we'll look at this in more detail. And coupling is checking to see if the design complies with axiom 1. So here's just an example of another example of a decomposition. So we talked about providing the high rotation speed. So there's the air spindle, downward motion. We can get that with a Haas. Locate the jigger to the workpiece. So we have the machine tool frame, and that is a locating system. So anyway, so the idea is here's 7 FRs, which we thought we needed to select in order to do a jig machine capacity on a Haas mini mill. And the design parameters. Well, the design parameters are what we're choosing to satisfy this, and you can see some of these things that were even dictated by the customer. All right, so let's go back and see what's FR7. Restrained motion to the Z direction. Bearing rail motion system. FR7, restrained motion to the Z direction. So restrain rotation about Y, restrained motion in X. I'm sorry. What we need to do first, though, is as we review a design, is look at just one level at a time. So we have 7. 7's decomposed into 7.1, 7.2, 7.3, 4, 5. And so now we have to look at those and say, are they semi-min? But what I want to do here really is not review this design in detail, is just show you how this can get expanded and how we go down to lower and lower levels, and there's even expand this, provide rail restraint in X. At the end of the design, though, what we want to get is the design intent recorded with the design. So we have these keys here. So we can go back and say, well, what was 6.4.2? And that tells me what that surface is. In a mechanical design, every surface and every member should have some kind of design intent attached to it. So here's what it actually looked like after machining. There it is in the machine tool. So it's actually realized as part of the summer undergraduate project. Now, one of the interesting things when we do manufacturing is that we can come up with some sort of product. Let's take our shaft, for example. So it's providing a seal and providing a sliding interface. The DPs, we're looking at some sort of topography. All right, to make those DPs, we might say, well, let's use a couple of grinding steps. All right, now, we're probably just going to go down to Saint-Gobain or buy some of the grinding wheels that we would need, or the grinding media, the grinding setup. Maybe we go to Sufina, buy a machine that's going to do this. And so many cases, everything we need is available commercially. However, supposing it weren't, supposing it's the late 1950s, early 1960s, and you're designing integrated circuits, and you say, all right, now we have to mask some areas and diffuse other material into the silicon. We need to cut the silicon up very carefully. We need to make it very smooth, and none of those machines are around. So the PVs that you would need, say for smoothing or chemical mechanical polishing, well, then we have to go down and do the tools. So the process that we need can be used to develop the kind of CNs, or more directly the FRs, for the tool. So how do we apply this process? Well, we need a tool to do it. And it is really tool design that sets our species apart largely. All right, and some of the most interesting things to find for archaeologists. All right, let's take a look at one more example. I think we're getting near the end. This came from a local company. They were doing centerless grinding. And so in centerless grinding, you've got a regulating wheel which provides friction against the workpiece. Here's the workpiece, this golden thing. And then G is the grinding wheel. So this is removing material, and it's held up on a blade. Now you can adjust this so the piece self-feeds through, but somebody needs to get it started by having the wheels at slightly different angles. Now, but somebody has to get this started. So somebody has to place it in there, and here was the problem. They were making a little tube for arthroscopic surgery that has a nibbler at the end. This is very sharp because it's made to cut up your cartilage or something once it gets inside you. So the person, they had somebody that was feeding these in, and they left. They've been feeding it by hand. They couldn't find anybody else that could do it because you've got a fairly large grinding wheel. It's whirling around, and this rubber wheel, and you think, Jesus, my hand gets caught in there. That could be terrible. And now I've got this thing with a sharp end on it, and I go, how am I going to feed that in there? And the person's just kind of dropping them in. And so if it's not fed properly and it gets a little crooked, it jams up, and the wheels have to be reset. And they were way behind in their orders since they lost the one person who was able to feed it by hand. So when I was called in, they were imagining some kind of multi-axis robot that they were going to buy, and then it would sort of have a hand kind of motion and pick this thing down and put it in the machine. And so they had thought that we'll need at least a month development. We'll have to spend some time selecting the machine. Then we've got to program it, and we've got some expertise. And all right. So what are the minimum number of FRs that we would need that are mutually exclusive, collectively exhaustive, in order to feed the part into the machine? So see if you can figure out, stop the video for a moment, see if you can figure out what the first or highest level FRs and DPs should be. So FR0 and FR1 and so forth. All right, if you didn't stop the video, then you're seeing a potential answer here. So you might want to try to avoid reading this, turn it off, and go back and do your exercise now. So here's what I propose. FR1 is going to be to align the part prior to insertion. FR2, maintain the alignment during insertion. FR3, protect the operator from the sharp end. So 1.1 then is going to be to somehow align the part with the holder and then align the holder with the machine. So align the part at X and Y prior to insertion. Well, you can do that with a little V block. And then align the holder with the machine. Well, so we do that with a special kind of slot that you'll have a special, very simple slot to maintain the alignment during the insertion. So a V front and back for the alignment here, a bracket, to maintain the holder with the machine, and a V block for maintaining it during insertion, and then FR3 protect the operator from the sharp end, we'll use a little push stick. So anyway, so there's an alternative set, and what it comes down to is still a V block and a push block. And so here's what the design looks like. There's the part, here's the V block, and there's a little push block. So I set this thing down and take the push block, push it up there, and then I can push it down that way, and then it engages the wheels are down here, and then when I push it in, it goes through and gets drawn in into the gap between the wheels and ends up doing a nice centerless grind on that part. So this simplified the design. And one of the neat things was, as we were working on this at the customer's location, the guy who was head of the shops sort of figured out, I see what I need to do. He excused himself and went and actually built the part and then came back with it. So this device was in production by the end of the day, and it was being used on several occasions by the employees of the company. All right, themes of mechanical design. What do mechanical designs have in common? One is controlling position, another is load transmission, another is motion control. And here's what happens. You can start off with those things on the upper level and then just keep decomposing until the solution is obvious. All right. So here's some guidelines. This should serve as a kind of checklist. I think we've covered all of this. There's no particular reason for them being out like this where you can choose any order you want. But that seemed logical for me when we did that. All right, most important takeaways. Good decompositions are essential to problem solving. Good decompositions are see-me-min. All right, so here's a little self-test again to go through at the end of this lecture. So what you want to do is take a look at these items and these lists and see if they are better as FRs, DPs, or constraints. And then here are two decompositions, provide orientation. Which one is better and why? And the next slide has the solution. So I suggest you stop your video, try to work out what you think these would best be, FRs, DPs, or constraints, and decide which one you think is better, and then turn the video back on. All right, so maybe now you have your video back on again, and let's see what happens. So there was my thoughts on what the right answers would be. And fastener is a DP, so that thing belongs out there. Some more Microsoft magic for realigning things. Great. Well, thank you very much for your attention. Thanks for your patience in there. Are you still there, or did you go home?